interested in the gory details of those errors, you can look at this paper, Beal et al. 2015. There's an entire appendix in which we look at the errors. But this is kind of a nice summary that hopefully shows you that the data is believable. We basically compared the current metadata at mooring G with the CPI's data either side, and you can see that the variability tracks very well with an agreement of R squared is 0.87 and a monthly timescale is 0.92. Okay, so the CPIs are working pretty well to give us those offshore estimates, and you can see them coming in here. And this is basically the movie that we got over 3 years.
Excuse me, what was the slope of your spectrum?
I'm sorry?
What was the slope of your spectrum which you showed?
Oh, I don't know. I didn't look at what the slope was. But from the 3 years, we didn't get a lot. I'll talk more about spectra when we look at the longer term proxy. But basically, both these spectra are, they're the same within 95% significance. And you can see that it's red. But other than that.
It's red on small landscape, but not red on large landscape.
No, on large length scales it looked pretty white, right? Okay. Okay, so here's the current. What I want you to notice about this is meander events. We'll have one coming up. Also, if you look at the zero ice attack here, you can see how a lot of the time there's quite a complex structure in it. Okay, so imagine if you're trying to define the jet and how it changes over time. It can have even a double core structure some of the time. You can see that kind of happening here. All right, and now we have a meander event. Here's the jet separated from the slope, and now it's coming back on shore. A lot of variance at short time scales. We found over a whole 3 years, we had 4 mesoscale meander events. This is just looking at the distance from the coast of the current core, okay, of the maximum velocity. These are the moorings AB through P4, P5. And we just said, well, okay, if the current has shifted more than 100 kilometers offshore, that's a mesoscale meander event. And you can see these events in sea surface height. Okay, here's 1, 2, 3, and 4. So these meanders come through as onshore cyclones, propagating downstream at around 15 kilometers per day, lasting on site at our site from 20 to 30 days. Okay. So during the meander event, we had this typical snapshot. This is actually from low ADCP data. We were lucky in 2010 to be putting the array in right during a meander event. That was pretty lucky because the meanders only occur about 10% of the time at any one place along the coast. And a more typical snapshot is this, where the current core is really hugging very tightly to the continental slope, and the maximum is almost right over the shelf break. And this is the mean that you saw before, the 3-year mean structure, where the width of the current is 220 kilometers in the mean, and the depth is around 3,000 meters. Okay, how am I doing for time? Is there a clock in here? Okay. So the next thing we're going to try is making a transport time series out of our 3 years. And ultimately, we want to take that in situ transport time series and extend it in time using that ground track data from the altimeter, okay, to get a proxy for how the Agulhas current is changing over time. We're looking to see whether we see that intensification over time that we think we might expect from the models and the sea surface temperature observations. So how do you create a transport time series of a western boundary current? Seems pretty simple, right? You just integrate across. And you could have a T-box where you just take the net transport from the coast to a point, let's say 220 kilometers offshore. That's our mean width of the current. So T-box is that transport at every time step. Okay? T-jet is where we try to create a transport that follows the current. Okay? So we saw those meander events as the current goes on and offshore. So what we want to do ideally is to try to follow the jet offshore and back onshore and look for just the transport in the jet. Okay? So just the poleward transport of the jet. So it took us a little time, but we came up with an algorithm for that. The simplest thing to do, you might think, would be to take the zero ice attacks on either side, right, and integrate from one to another, and just take the southwestward flow. But often, you don't have a zero ice attack crossing the surface on the offshore side. So what we did was we defined T-jet as the poleward transport out to the first maximum of the transport per unit distance beyond the half width of the jet. Right? That's a bit of a mouthful, so I tried to draw up this to help. So for example, T-box is out to the silver star and T-jet is out to the red star. So if you have a situation where the Agulhas current, where the transport per unit distance looks like this, where it's narrowed on average, so here's the half width of the jet, 110 kilometers. Here's the mean width, 220 kilometers. T-box is always going to be the integral out to 220. In this case, the maximum of Tx beyond the half width, okay, is here. And so we would integrate out to there for the jet transport. If you imagine you have a case where you have a wider than typical jet, T-box, we still integrate net out to here. And now T-jet, we're going to go farther offshore, okay, and account for this widening. And if we have a meandering, then again, T-box would be the net, so it would include the northward flow and the southward flow, but it would miss this southward flow out beyond 220 kilometers, while T-jet would not include the northward flow. It would just integrate across the southward flow out to this second maximum is the first maximum. That's why we had to put that caveat in offshore, okay? So you get the idea. It's trying to objectively come up with an algorithm which basically follows this jet as it meanders across the array. So what we get is a time series that looks like this. So T-jet is in red. T-box is in gray. These gray lines, again, are the times of those big mesoscale meanders. What you can see is that during this mesoscale meander, for example, you've got massive changes in the transport which are opposite between T-box and T-jet. And that's because with T-box, you're accounting for all this northward flow, but you're cutting off a lot of the jet because you're only going out to 220 kilometers offshore. With T-jet, you're not counting the northward flow, and you're capturing all this southward flow. So there's arguments, you know, for one or the other measure. I would argue that T-jet is trying to remove a lot of the eddy variability, right, and just concentrate on the transport variability, the true transport variability in streamwise coordinates. That's what we're really trying to do here. So what we find is that then we have a mean transport of 84 sphere drops from T-jet and 77 from T-box. And again, these goes into the some of the statistics, and I encourage you to look at the paper if you're interested in more of those. So does that seem sensible for a mean transport? So we have other transport array that was deployed at 32 South during WOS back in 1995. It was five moorings out to about 150 kilometers offshore. It did not capture the meander events. Okay. However, Broadening created a definition For the transport, it was basically a T-box-like definition where he integrated over the width of the current and down to 200 meters below its mean depth to get a transport of 70 Sverdrups. So we did the exact equivalent transport at the ACT array to try to get what the increase is, and we found a mean transport of 79 Sverdrups. And if you look at the increase of the Sverdrup transport from the winds over that region, then you get about the same, a 9 Sverdrup increase, okay? So this is about 2.4 Sverdrups per 100 kilometer downstream, increase in transport, and about equivalent to the Sverdrup transport predicted by the winds. So the implication is this is quite a different system, say, from Gulf Stream increase in transport, where most of the increase is related to a recirculation of the current. The dominant variance in the Agulhas is those meanders. And so briefly, just showing you you can see that in this EOF analysis. So we looked at the eigenmodes of the velocity data from our 3 years. And we find the leading eigenmode is basically, looks like a meander mode. And indeed, the second and third eigenmodes also, with increasing number of nodes, okay, relate to shifting on and offshore of the jet. And then the fourth mode you can think of as more like a transport mode. So in this case, the whole cross-section is either strengthening or weakening, like a pulsing, okay? And this EOF4 correlates very strongly with T-box, the transport. And if you look at the principal component time series, what you see is that for each meander event, first of all, you get principal component time series 3 peaks. So what's going on here is the current actually moves onshore, shifts onshore first at the very front of that meander event. And then it shifts offshore. Okay, this would be the peak of the meander event, so EOF1 peak second, and then finally EOF2 peaks when the current's starting to come back onshore. So it takes these 3 eigenmodes to describe this mesoscale meandering process. Or you could look at a rotary eigenmode, and this single rotary eigenmode basically picks up that meandering process by taking into account phase changes. Okay, and then you begin. This is a pretty complicated picture. This is the phase change in the colors. So you can see a phase change from about the mid-jet on and offshore over time. And what's happening is that there's basically a cyclonic rotation in the gray, clockwise rotation on the inshore side of the jet over time, and an anti-clockwise rotation of the current vectors over time on the offshore side of the jet as the meander comes through the array. Okay, so moving on, how can we build a proxy? We want to try to relate this in situ data of transport variability to the sea surface, because that's where we have 20 years of satellite altimeter data along the array. And so first of all, we looked at if the sea surface height is varying in the same way as the transport in the array. So what this shows is the first 4 eigenmodes of sea surface height, or absolute dynamic topography, at the top, and sea surface slope at the bottom, compared to the first 4 modes of Tx, the transport per unit distance, or vertically integrated velocity, from each of our moorings, which are in the dotted lines here. So what I hope you can see is that we have similar variance. For example, EOF1 from the combined sea surface slope and sea surface looks like a strengthening. So here we have, in the red is the anomaly, the black is the mean sea surface slope. This is the negative sea surface slope, so it's easy to compare with the transport, which is southward. and the blue is the anomaly plus the mean. So it gives you an idea of what it's doing to the jet. So in this case, you've got a strengthening of the jet, okay, which looks the same as this EOF2 from the in situ data, a strengthening of the jet. In these cases, you have a narrowing or broadening of the jet. Okay, you can see the blue is a narrowing of the jet in terms of this sea surface height anomaly across the array. And then you have a couple of more modes, which basically are meandering of the jet. So you can see here the jet's moving onshore, here the jet's moving offshore, and we have very similar modes with the sea surface height. So this was good. This looks like we have similar variance, and so we have a chance for the proxy to capture what's going on with the transport variability, full depth in the ocean. So we built a proxy based on the regression of the local sea surface slope at each of the 9 moorings. There's a number of ways you could build proxies. We tried 3 different ways. And if you're interested in some of the details of that, ask me afterwards. And it'll become clear why I'm showing you and why we needed to go to this technique. So what we did is, this is what we called the physical technique. So this is basically thinking of, geostrophic velocity from sea surface slope at each of the 9 moorings can be related to the transport at that mooring. So we regress the local sea surface slope against the vertically integrated cross-track velocity from each mooring. In doing that, we chose dx. How do you choose over what dimension you calculate slope? So we actually use the mathematics to find what the maximum correlation, trying a bunch of different dx's, is between the sea surface slope and the in situ vertically integrated velocity. And we came up with, we backed out then what dx should be. And basically it varies from about 27 kilometers closest to the coast to 100 kilometers farthest offshore. So that makes sense. We would expect the physical scales of the flow to be growing as we go offshore. So this is what we get. This is the T-jet proxy, and this is the boundary or T-box proxy. You can see that we compared it to the in situ transport, okay, over the time of the 3 years of the array. And we got R at 0.74 and 0.78, not too bad. So it explains about 50% of the variance over the 3 years of the in situ data. And then you can see the spectra here. Now with the jet, we have less variance, less power at longer timescales, which is interesting. Maybe there's a potential that the jet has removed some of the noise at these longer timescales by trying to remove that eddy variability from the shifting of the jet. And we have a significant annual peak. And that annual peak, the seasonality in transport looks like this. Here's the jet, and here's the T-box, and here's T-jet. So they have exactly the same seasonality, whereby the current is strongest in austral summer and weakest in austral winter. But T-jet has half the amplitude of T-box. I don't exactly understand that, but that's what we find. And we did put a trend on these, and we found that the resulting trends in T-jet and T-box over time are not significant. So you'll remember that we were expecting that this current might be intensifying over time, and we don't find that. And so the question is, how do we know this proxy is robust? Right? We could create another proxy, for instance, which is perhaps more common, where we look at the sea surface, the change in sea surface slope across the whole array compared to the transport across the whole array, okay? And we might also create a proxy where we use those where we use those eigenmodes to regress against, so the eigenmodes of transport to regress against the sea level variability. So how do we know this one is robust? So we looked at what the trend in the sea level and the sea surface slope is over time. So what this shows, this is from two products, Aviso and the new CCI, which is supposed to be particularly good for looking at long-term changes. And you'll see that both of these data sets show a sea level trend, which is a maximum at the flanks of the current and a minimum near the jet core. And if you look at what that means for sea surface slope, remembering that sea surface slope is everywhere positive across the Agulhas Current, then the slope is weakening inshore and strengthening offshore. And what that means for the proxy in transport, it translates basically, so if you look at, say, T-box in the gray over time, the solid line is from the beginning of the time series, and the dashed line is from the end, okay? So what you're seeing is a weakening and a broadening of the jet over time. So the Agulhas Current is weakening and broadening. It's not intensifying, it's weakening and broadening. The core of the jet is weakening, and the flanks of the jet, the slope is strengthening, with the transport unchanging. So what that means is that a fixed integration, T-box, can't account for this change because you're not allowing T-box to change in its width over time, right? So it can't account for a current that might be broadening over time. And it also means that a proxy based on total transport isn't reliable, right? And that's what we tried first. And we got spurious trends which didn't match what's going on when you look closely at the sea level at all. And that's because if you basically look at total transport, you're doing the same thing. You're basically only allowing the variance to change, within a set distance of the coast. You've got to choose your slope between 2 points, basically, right? In our case, we can allow this broadening and narrowing over time because we have 9 points where the sea level, where the sea surface slope can vary differently, basically. So I guess the take-home message here is that the slope of the sea surface across a western boundary current is not the same everywhere. And that difference can be important in terms of how it's changing over time. So how do we understand a broadening of the current? Well, we can simply think about very simple dynamics such as a monk boundary layer. If a monk boundary layer is